Okay, in this video I decided to lump together amides and nitriles all in the same grouping here. So how would we name this molecule here? This is a derivative of acetic acid. Okay, so it's going to be an acetamide derivative, and we want to take a look at what functional groups are attached to the nitrogen. There's a methyl and an ethyl. Ethyl is abbreviated first, then N-methyl, and yes, you need a nitrogen for each one, or else we might think that there's methyls or ethyls attached to the carbon framework that makes up the rest of the molecule, and this would be called acetamide. When you're naming molecules that have the nitrile functional group, you need to count that carbon as carbon 1, or count it as being a carbon. So this is going to be butane nitrile, okay? Now, if you have something like this, you could name this butane nitrile with the methyl group at carbon 2. So you could name this as 2-methyl butane nitrile. Okay. Obviously, the nitrile is at carbon 1, so it's redundant to say 1-butane nitrile. Now, if you have a more complicated molecule and you're not sure really how to name the longest chain or something like that, you could name this as a cyano group. Okay, a cyano group. So we could call this 1-cyano such, okay? So this would be, I think it would actually be, the alcohol would be at carbon 1, so we would call this 3-cyano cyclo pentanol. Okay. Another example where you might not be sure how to name this. That's the cyano group, so you could call this cyanobenzene. We don't need a number here because there's just one thing attached, okay? So yeah, that's the nitrile. Now let me talk about reductions of amides. So if you have an amide, and we've talked previously about hydrolysis, right? You add water, some concentrated acid, and you heat it up to boiling for quite a while. You form the carboxylic acid, and the amine is separated, right? Removed through the hydrolysis reaction. If you have, so this has 4 carbons, just want to kind of be systematic here. If you have a nitrile, which is in a sense a carboxylic acid derivative, and you treat this with water, acid, and you reflux, and you take it all the way to the end of the reaction, you're going to form a carboxylic acid that has the same number of carbons, and you're going to split off the ammonia here, okay? And we've already talked about the synthesis of carboxylic acids with the use of nitriles. Remember, these come from primary or secondary alkyl halides and sodium cyanide, okay? The hydrolysis reaction of nitriles, let me just show you how that works. It's going to work in a very similar way to what we saw previously about the hydrolysis of amides. So let me show you the curved arrow reaction mechanism for this right here. The nitrogen has a lone pair. It's kind of hidden there, but if you draw out the dots, you can see it's there. And this is going to be a strong or good electrophile. And water can attack the carbon, and electrons go to the nitrogen positive charge. So it's starting to look like a carboxylic acid now. Remember again, the goal is to remove this nitrogen as maybe a molecule of ammonia. So what we need to do is keep deprotonating and moving the proton around to the nitrogen. So here's water. It's going to deprotonate. Oops, protonation happens here, attack happens here. Okay, so we want to deprotonate here. And, you know, we form H3O plus. And then the nitrogen becomes protonated. So the usual proton transfer is a couple of steps. So that's going to be P for protonation. And then we're going to have a thing that looks a lot like an aminium ion. Now, this guy here, I normally like to show it as a separate step here, so we'll do that. This is a, you know, we can draw a resonance structure here. And I just want to kind of we don't need to show this step, but I just wanted to show you that this now is looking a lot like a carboxylic acid. Okay. Now it doesn't. I'll just put this in off to the side here, and that's the resonance structure. But what we want to do here is use water, which is the nucleophile here. And we could attack this resonance structure, or we could attack this other resonance structure. Okay. Either way, you're going to get this molecule here. And remember again, we want to kick that guy off. To do that, so that step right there is the attack step. Okay. Either what we need to do is now is deprotonate this guy here. Okay, and then this guy here needs to pick up an H plus. So another a couple steps of proton transfers. And then this finally will give us this molecule here, and you can see how ammonia is ready to be spit out of this molecule by the assistance of one of these oxygen atoms with its lone pair. And so that's the elimination step. And we get our typical protonated carboxylic acid, and water can come in. Or you could have ammonia, right? This is under acid conditions, so ammonia is going to be protonated. We can more easily show that protonation step by combining it with the last step of this mechanism. So ammonia can come in and deprotonate, and that gives us a carboxylic acid and the ammonium molecule, NH. 4 plus, okay? So let's look at what has occurred here. We have protonation, then attack, then deprotonation, then protonation, attack, deprotonation, and then protonation, then eliminate, then deprotonation. This is one of the longer mechanisms. So that's pad, pad, ped. Okay. Yeah, so that's where I wanted to talk about that. So that's hydrolysis of nitriles. So now I wanted to talk about reduction of amides. Now it doesn't matter if it's primary or secondary or tertiary. Amides are very unreactive, so they basically only react with lithium aluminum hydride and water, or LaH and H2O, as we like to abbreviate lithium aluminum hydride. And to draw the reaction products, you basically just want to erase the carbon-oxygen double bond. So we would draw the products here like this. Okay. From a secondary amide, we form a secondary amine. And in this example down here, we would transform our primary amide to our primary amine. Do not worry about the mechanism. Okay, the mechanism is not in the standard group of very similar mechanisms, so I normally don't require my students to memorize this. Okay, nitriles also react with lithium aluminum hydride to give amines. And I just wanted to make sure people understand and carefully look. This has 4 carbons. This has 4 carbons. Okay? So if you see something written like this, and you treat this with lithium aluminum hydride, don't just write this, because this is a molecule that has 1 less carbon. Okay? Don't draw that. Draw this guy here. Okay? Where you have that carbon atom right here still in your molecule, okay? And I'm just pointing out what I've seen a lot of students get a little confused with in the past, okay? So that's the reduction of amides and the reduction of nitriles, okay? And I think that is most of what I want to talk about with the amides.